Hello, welcome to Fundamentals of Acoustics. Today is the 5th day of the current week, which is the 9th week of this course. And just yesterday we started discussing time and frequency domain representations of signals. And what we had shown was that if we can depict a signal into its, if there is a signal which is composed of sines and cosines only, then we can depict that signal either in a time domain or in a frequency domain, and from such representations, those graphical representations, especially the frequency domain representations, we can extract the frequency and phase associated with each frequency component of the signal. So, what we plan to do today is figure out how do we mathematically convert a periodic signal into its frequency domain representation. So, I will explain that. So, what we will learn today is how to convert a periodic signal from time domain into frequency domain. This is our aim. So, please note that I have used the term periodic signal. So, that means that the signal has a specific period, but it may not be harmonic in nature. So, what does that mean? So, I will draw a couple of periodic signals. So, this is one periodic signal. Another periodic signal is this. And so on and so forth. So, this signal repeats itself after every t seconds. The nature of the signal is identical after every t seconds. So, this is another periodic signal. So, this is signal type 1, which is purely harmonic. So, I can express right away just by looking at it into its sine and cosine terms. But this second signal is periodic, and it will be really nice if we can somehow convert this type of periodic signal into a sum of sines and cosines, because the moment I convert it into sum of its sines and cosines, I can then use that conversion and get a frequency domain representation of the signal. So, our problem is how do we convert especially this type 2 signal into a sum of sines and cosine, because the moment I convert it into sine and cosine, then I have amplitude of each sine and cosine term and phase, and then that I can plot it on a graph for an amplitude plot and a phase plot. So, how do we do that? So, you must have learnt this technique, that if there is a signal which is periodic, okay, it is important, which is periodic and is piecewise continuous. So, what does piecewise continuous mean? See, this signal is continuous in this piece, and it is also continuous in this region, and it is also continuous in this region. Another periodic signal could be this. So, it is like this, 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 this. So, at these points the signal is not continuous. So, this is type 3 signal, right. So, signal 1 and 2 are continuous because the value is continuous at all points, it has only single value, but in signal 3 at these transition points the value is not continuous. If I look at it from right side, from the left side the value is 0, if I look at it from the right side the value is non-zero. But even type 3 signal is continuous because it is continuous in piece 1, it is continuous in piece 2, it is continuous in piece 3, it is continuous in piece 4. So, that is what is the meaning of piecewise continuous. Okay. So, if there is a signal which is periodic, so type 3 signal is also periodic, same is type 2, same is type 1, and if it is piecewise continuous, then we have learnt in our earlier years of mathematics and engineering that this so, and if it is piecewise then it can be expressed as a sum of sines and cosine functions. So, it should be sine, it is a sum of sine and cosine functions, and this representation of the signal is known as Fourier series. It is known as Fourier series. So, what does that mean? That if there is a periodic signal, suppose this is the time domain representation, so this is f t, and let us say the signal looks something like this. This is a periodic signal. Then this f t I can represent it as a sum of 3 parts, a constant a naught plus a sum of cosines a n cosine n t plus b n sin n t, where n equals 1 to infinity, n equals 1 to infinity. Okay. So, if there is a periodic signal represented by f t, then it can be expressed as a naught plus a sum of cosine terms plus a sum of sine terms. Now, this relation works if the time period of this signal, time period, so time period is equal to 2 pi seconds. So, what does that mean? So, how do I depict time period on this? This is the time period of the signal. Okay. So, this is the simplest form of a periodic signal. Later we will generalize it, that whatever is the time period we can develop an expression for this. So, that is our time period. So, if the time period is equal to 2 pi, then I can represent this signal as a naught plus a n cosine n t plus b n sin n t, where n is an integer and it does not start from 0, it starts from 1 and it can go up to infinity. Okay. So, then our aim is how to find what are the values of these parameters a0, an, bn, because the moment I know a0, an, bn, I also know n is just changing 1 to infinity. So, I can express f t as its Fourier series. So, a0 . finding A0. So, how do I find it? What I do is I multiply this expression. So, let us call this expression 1. So, I multiply its left side and right side by 1 or basically essentially I integrate the left side as well as right side with respect to time over the time period, and when I equate them I will see that I end up with an expression for A0. So, let us do that. So, what is the time period? 2 pi. So, I integrate it from minus pi to plus pi f t dt, and that equals integral of minus pi to plus pi a naught dt plus minus pi to plus pi sum of a n cosine n t dt plus third integral minus pi to pi b n sin n t dt, and here n is equal to 1 to infinity, here also it is 1 to infinity. Okay. So, so if I know this function f, then I can evaluate the left side, and what is the right side? This is equal to A0 times 2 pi plus, let us look at this. So, the integral of cosine n t is sin n t divided by n, and sin n t evaluated at pi is 0 and sin n t evaluated at minus pi is 0. So, this is 0 plus integral of sin n t is cosine n t divided by n into minus 1, and the value of cosine of pi is same as value of cosine of minus pi. So, when I take the difference, this also becomes 0. So, A0 equals 1 over 2 pi f t dt minus pi to pi. So, this is my expression for A0. Okay. So, the next aim is that we want to find an. So, what do we do if we have to find an? I multiply equation 1 on both sides by cosine m t. Instead of n, I put another index m. M is some dummy number, okay, and I do the integration, and let us see what happens. So, minus pi to pi f t cosine m t dt, this equals minus pi to pi A0 cosine m t dt plus minus pi to pi sum of a n cosine n t cosine m t dt plus integral minus pi to pi b n, oh there is an integral sign also here as a summation sin n t cosine m t dt. So, this equals, what is the integral of cosine m t? Sin n t, when I evaluated pi and minus pi, I get 0. Okay. So, the contribution from the first term is 0 plus, now cosine n t times cosine m t, there is a trigonometric relation that cosine A times cosine B is equal to what? Cosine A plus B plus cosine A minus B. So, we do that. So, this is summation of, I will actually erase it, first write a n cosine n minus m t plus cosine n plus m t dt plus integral of minus pi to pi summation of, so this goes from 1 to infinity bn, and this is sin n plus m t plus sin n minus m t dt. Okay. So, what is the contribution from this term? So, sin n plus m t, if I integrate, it becomes minus cosine n plus m t divided by n plus m, and if at time t is equal to pi and time t is equal to minus pi, the values are going to be same because cosine theta equals cosine minus theta. So, contribution from this term is 0, contribution from this term is 0 for the same reason. So, the only thing which is going to contribute is this term. So, we will a n, and this is in parenthesis, sin n minus m t divided by n minus m plus sin n plus m t divided by n plus m, and this is evaluated at minus pi and pi. Now, look at the second term, sine of the denominator of this sin n plus m t is always a non-zero number, n plus m is non-zero. So, the denominator will always be non-zero. The numerator, when t is equal to pi and n and m are integers, it will be 0. When n and m are, and for n and m being integers, when t is equal to minus pi also, it will be 0. So, this is 0 because denominator is always 0. Now, look at this guy. Okay. This is interesting. When n minus m, okay. So, when n minus m is not 0, when n minus m is not 0, then there will be, the denominator will be non-zero number. What will happen to numerator? Consider the case, so when the numerator will always be 0, right? Numerator is always 0. Let us say n is equal to 2, m is equal to 1, sine of pi minus sine of minus pi, it will be 0. So, this green term is 0. When n is equal to m, then what happens? I have 0 in the numerator and I have 0 in the denominator. So, I cannot calculate its value. So, how do I calculate the value? I calculate its value using L'Hopital rule. And we find that when n equals m, then this term in the green is not 0. We find that it is not 0. So, in that case, so if I can calculate this term, so when n is equal to m, so for all values of m when n is not equal to m, this thing will be 0, right. When n is equal to m, only for that n I will calculate the value of a n, all other parameters they will go away. So, I can write it as that a n is equal to, so this is equal to, and when n is equal to m, when we use the L'Hopital rule, we find that this entire thing it becomes, so actually this entire thing this entire thing, it becomes an over 2 times pi. This is what we get out of it. Okay. So, what do I get? So, an, excuse me, so an equals 1 over pi integral minus pi to pi f t cosine n t dt. This is what I get out of it. Okay. Actually, this 2 should not be here. And if I do the similar mathematics, so if I have to calculate Bn, what do I do? I multiply this original equation 1 both sides, left and right side, by by sine mt, and I do the integration, and I will find that I am left with only one term, and using that I get the expression Bn equals 1 over pi minus pi to pi f t sine n t dt. Okay. So, these are the expressions. So, and then A0 we had already shown is equal to 1 over 2 pi minus pi to pi f t dt. So, these relations work. So, using these values of A, we can break any function, we can break any. So, using these relations, any f t, and this f t has to be piecewise continuous it has to be periodic such that its time period is 2 pi. So, any function which is piecewise continuous and periodic with a periodicity t is equal to 2 pi, any relation f t can be resolved in terms of sine n t and cosine n t. Okay. And the moment we get each component, each sine n t and cosine n t, for each of these frequencies I can calculate its magnitude and its phase. How do I calculate magnitude? By a n square plus b n square, the whole thing under square root. And how do I calculate phase? It is tan inverse of b n over a n. So, the moment I get this type of a representation, I can calculate for each frequency its phase and amplitude, and those phases and amplitudes I can plot on a in frequency domain in a amplitude plot and a phase plot, and I can represent the function as in the frequency domain. So, that is why we are doing all this. Okay. Now, but here the only limitation is that t has to be 2 pi. Now, what we will do in the next class is we will expand our scope and we will say how we can represent the signal if it is periodic, but the time period need not be 2 pi seconds. Then how do we transform it, and then we will do an example. So, with that we close the discussion for today, and I look forward to seeing all of you tomorrow. Thank you.